Kristen, how long do you need? It's now, so.
A few seconds.
Sorry?
A few seconds.
Okay, so I'll talk for a few moments, so.
A lot of slides today.
Okay, so welcome to 22nd C++ London Uni class. We close that. So the music is not recorded and YouTube will not
Kick us off again.
yeah, block our content. Sorry, Laura. Thank you. YouTube. Listening in the background, and if they detect any songs, they block the contents. So
Even for educational purpose, because usually you send your notification and you can object, and if it is for educational, I should know.
we had one class in the main room, yes, and there was lots of songs going one after another. To us, that's a white noise, like a background noise, which basically disturbs, not helps. Definitely, we were not listening sounds. We didn't care about this, it was disturbing, but it was rejected and they said, no, whatever we will take you to court, we'll bankrupt you, we'll kill you and all your descendants 20 generations down. So
That's exactly what they said. Yeah,
yes.
That was literally what the email said.
Exactly, so no. So going back to C++ London, it's our 22nd class. We're getting slowly towards the end of this edition of the course, but that means, as you know, we will be restarting the course in May. So the idea is the 1st of May, which is Tuesday, there will be a first class and we'll roll on. The idea at the moment is we're considering one or two books, and Tristan, together with Ollie, they will decide which book actually we will pick. So the idea is behind it, so you can read the books, in advance, chapter by chapter, or whatever the order that we decide it will be, and from there, basically follow up the classes. Now, at the end of this course, yes, and as well on the other one, we will definitely do the tests. So once people go through the course, they have a chance to pass. If they do pass, they will get the certificate from us. The idea behind this is to create fairly tough course. It will be, as far as we know at the moment, as it stands, it will be project-based. So basically, people will get a project, and they will have to complete that project, and obviously then tell us, how they built, what was the idea behind it. Not me, because I'm not qualified for that.
It's not mandatory, by the way. This is an.
Oh yeah. But obviously, if you want to have it like a full benefit, so next time you apply for, let's say, job or something like that for promotion, you can use this as an extra bonus point to show that you're actually doing something else. Our standard stuff, our website is cpplondonuni.com. You're very welcome to join us there, subscribe. If you do subscribe, then it's easier for me to get in touch with you, let you know what's happening. Slack, obviously, and every week we are here. Pretty much we booked for another few months. I think there's only one class which will not be happening here.
Yeah, Yeah.
So it will be most likely a poly place. Apart from that, that's from me all. I hope you enjoy today we'll be talking about algorithms.
Well, mostly about containers and complexity and things. A little bit about algorithms at the end. Then you're going to have fun implementing some algorithms. Okay, standard. I won't bother with that. You've all seen that, but it's on the slides for other people who might be looking at this. So this is what we're going to do. So last week, everyone was here last week, man. Yeah. So everyone won't really need to bother going over the iterators revision. That was in case we had anybody who couldn't make it. Lauren, you weren't there last week.
Yeah.
Okay, well, we'll go over that pretty quickly. And then we're going to talk about algorithm complexity because, again, for Lauren, this was something he requested quite a while ago. So we'll have an introduction to that. I can't promise to really go into depth with it. But then we'll have a quick overview of the different containers that are in the standard library and when you should choose to use each one. Come in. And then we'll have a brief talk about algorithms as well. And then there's as I say, sorry? A coffee would be fantastic. Just a coffee would be lovely, thank you. Yeah, and then there's an exercise where you can implement some algorithms in this sort of standard library style to get a bit of practice using iterators and how you put together an algorithm. Just a little bit of milk and some sugar would be lovely, thank you. And put my drinks order in. Excellent. Okay. The one guy who didn't see this last week has just left the room. So, oh, you weren't here last week either. Okay. So the standard template library was invented by this gentleman Alexander Stepanov in the early 90s. He was working at HP Labs. And it provides a set of container classes and algorithms that operate on these containers. Except they don't really operate on the containers. What they operate on, the algorithms operate on iterators, which is what the containers give you. And this is all just revision from last week. But so the STL really, the library pioneered this idea of something called generic programming. Really completely changed the way that people looked at C++, because before that it was really seen as just an object-oriented language. That's how it started, a set of object-oriented extensions to C, and Stepanov kind of transformed the way people looked at templates and the way you could put together software. So it's a really big deal at the time. In '94, I think it was published. And so this early standard template library, the STL, was released to the general public by HP, and it formed much of the C++ standard library when that was first released in 1998. To the extent that even today it's really common to refer to the containers and algorithms as the STL, even though it's technically incorrect and pedantic people will.
Because there are not many of those in IT, are there?
Yeah, pedantic people will have a penny for it, but yes, exactly. Thank you very much. Right, caffeine, this is going to get me through. Get me through this if I don't spill it on my laptop. Okay, so this is just a couple of slides of revision from last week. So iterators are the glue, if you like, that bind together the algorithms and the containers. So as I said, algorithms don't operate on containers directly, rather they operate on iterators, which containers produce. An iterator, one way of looking at it anyway, is that it represents a position in a sequence. So you can ask for an iterator to the beginning of a container, an iterator at the end of a container, or actually one past the end, we'll talk about in a minute. And then you apply an algorithm to these iterators.
Sorry, you mentioned that iterators are produced by a container. It means when I create a container, it also creates iterators like begin and end.
Well, when you call, so you create a container and then it has methods .begin and .end
For example,
that give you the iterators.
Okay.
Yeah.
Okay, okay. So when I initialize it, I also get them.
Yes.
Okay.
Yeah.
But other than begin and end, there are others that I should be aware of.
There are a few specialized ones that I can't remember off the top of my head. Standard regex has some special iterators, for example. There are other ones, but mostly you get them from containers.
Can you remind the difference between the STD begin and the begin?
And member begin. Okay, so STD begin was introduced in C++ 11. If you pass it the name of a container instance, if you say standard begin my vector, then it will just call vector.begin for you. So you say, well, what's the point of that? It's because you can also pass a raw C array to standard begin, which there's not much need for it. You should be using standard array instead. But for really generic code, it can be good to call standard begin. There's also another class called standard val array, which I won't really talk about today, but it has begin and end defined on it. So as I said, an iterator represents a position in a sequence. It knows a position and it knows the sequence that it comes from. And we can dereference, it's called dereferencing. We can dereference an iterator to access the element that it points to, and we can advance the iterator. These are the very basic operations. We can advance the iterator so that it moves to the next position. And I didn't say it because I'm silly, but you could also compare two iterators. You say, are these equal? And they're equal if they point to the same element of the same collection. Okay? So for you guys, this went on this length last week. I'm racing through it for Laurent, who may or may not have looked at my slides last week. I don't know.
Yeah, quickly.
Yeah.
The main difference between a normal pointer and the iterator?
So a pointer, or a pointer into an array, that is a kind of iterator. So there's no class called iterator. Well, there is, sort of, but ignore it because it's going away. An iterator is a generic concept. So anything for which you can do these things, anything that you can dereference and advance and compare for equality and a few other requirements, anything that you can do those operations to is an iterator. And it just so happens that you can perform those operations on a raw pointer. In fact, that's really where these operations came from, is by looking at what the pointers do and how can we generalize that. So I've said here an iterator represents a position in a sequence. Another way of looking at iterators is that they're a generalization of pointers. So
just one question about equality.
Yeah.
When you compare iterators, you're comparing the values to the actual.
No. You're comparing whether they point to the same thing. Okay. So if you imagine you had a vector that contained, it was a vector of ints and it was 2, 2, 2, 2, 2, 2, 2. Right? So it contains 2s. That's all it has. You can have two iterators that point to different positions.
Yes.
They're different, so they compare different, they point to different elements, but the values that happen to be in those positions are the same.
Right.
Does that make sense?
Yes.
If there was a whiteboard, this would be
that makes sense. So I'm saying you're comparing the values.
No, you're comparing the position in the sequence, not the values.
Not the values. Okay.
Yeah. Have we got people online, though?
Yes, we do.
Oh, excellent.
There
Well,
is,
if anybody asks any
at
questions.
the moment is, yeah, I'm keeping an eye on. At the moment we have 4 people.
All right. Hello, everybody.
Everybody, it's 4 people.
Yeah, everybody. So algorithms operate on iterator pairs. So all the standard algorithms, you'll see they take 2 iterators. Normally they call them first and last. And the first iterator points to the beginning of the sequence. I'm going to draw this nice little diagram on this very handy piece of paper. The first, if you call begin, it points there. So let's say this was a vector that contained 1, 2, and 3. When we call end, what it returns to us is a special value that's off the end of the array. So if this was a vector that contained 3 elements, when you call end, what you get is this special extra thing on the end. So,
But that's not part of the vector.
That's not part of the vector. It's a special like terminator, if you like. I'll be back. Yeah. So in mathematical terms, we'd say this is a half open range. So it includes begin, but it doesn't include end. And this is pretty good in a number of ways because it lets you, for example, if you're writing a find algorithm, so you're searching in a container for a value, what do you do if that value is not there? Well, what you do is you return end. You return this position that says, I'm not part of the sequence.
Does that?
You turn the board for the...
Yeah, I know. Sorry, people online, you can't actually see the board that I'm drawing on.
I will put the photo
So does that imply when you initialize the memory with a vector of the array, you have to initialize an extra space for the terminator?
For some containers you do. It happens that there are special rules in the language with regard to language level arrays, so that you're allowed to look one past the end of the array.
Okay.
Pretty much especially for this case. Or to put it another way, iterators are designed like this because the C language had that special rule.
But which containers do you have to declare the extra space for?
So if you have a linked list, for example, so your end iterator, so if you probably must have implemented a linked list in whatever programming language you learn, the extra one, you have like a node type and it contains a pointer to the next node, contains a pointer to the next node, and so on. And your final one's just going to point to null pointer. That's how you know you've reached the end of the list. So your end, in that case, would probably return a special sentinel node that didn't point to anything.
But you don't have to create that. You don't have to, as the programmer, have to actually create that.
I don't think you do in that case. I'm trying to think of a container implementation where you'd have to do it specially, and I can't think of one off the top of my head.
Okay. I don't know.
No, it's a good question. So, yes, you pass begin and end to the algorithms, but you can also give it a subsequence. Let's just say you only wanted to sort the first 5 elements of a 20-element vector, but you only wanted to sort the first 5 elements for some reason. You could just pass it an iterator to the first one, an iterator to the 6th element, because of one passed, and then that would just sort the first 5. So this thing of having iterator pairs lets you operate on sub-ranges as well. You don't have to operate on the whole container. That said, if you have used the standard algorithms, you'll know it can be quite wordy because you have to, repeat the container and type .begin and .end. There's a lot of typing involved, and for that reason, there's a lot of work underway in the standard library to allow you to just say this. It won't necessarily be in the namespace standard ranges. It might be. They don't know yet, but so that you could just pass the name of the container once, and it would do the sort on the whole container. It would call begin and end for you in that overload.
Repeat the question from the group.
Oh, sure. I didn't know it wasn't picked up on the microphone. Yeah. So the question was about the are there containers for which you have to implement end specially? And there probably are, but I can't think of them off the top of my head.
Can you apply an algorithm on several vectors or several containers at once? Like the...
So
in geometry, like the scalar product of two vectors.
Okay, so so the question is, can you apply an algorithm to several vectors or several containers at once?
You need to write it yourself.
Yeah, you'd have to write it yourself. So there are some algorithms, such as transform is one of them, equal is another one, and standard accumulate as well. And they take two ranges. So for example, standard transform, what it does is it takes 2 ranges and a function, and it takes an element from the first container, an element from the second container, and applies the function to those, and it puts the result in a third sequence. Yeah. So algorithms don't necessarily just operate on one sequence. You can give them, there are some algorithms that operate on 2 sequences. I don't think there are any that operate on more than that. Yeah?
So far so good.
Okay. So again, this was last week. If you want to, there's the videos online if you want a bit more detail, because we're rushing through it a bit here. But there are 5 categories of iterators. It's only 4 lines with input and output. And they form a hierarchy. So input and output iterators are the really basic kinds. They're what are called single pass. So that means we can only dereference them once. Once we've looked at the value of this iterator, we can't do that again. That value is gone. It's disappeared into the ether. So if you think about something like if you're iterating over a file stream, you might read the value, but trying to go back in this sequence might be really expensive, because you have to go back to the disk and, back in the old days, physically move the head of your hard drive. Going backwards is really expensive, so you wouldn't implement bidirectional iterators for a file stream. So input-output are they're the really basic ones. So input iterators are the ones we can read from once. Output iterators are the ones we can write to once. And then we have forward iterators, which have the same operations as input or output, except that they're multi-pass, which means we can dereference them more than once and get the same value.
And now, with modern hardware, moving forward, backward, or randomly, is it more or less the same in performances, or they still?
Well, with the file streams, you can memory map the file, and then you get effectively random access. But at the operating system level, it's still going to do some buffering, and if you read from outside this buffer, it's going to be slow because it has to go back to your disk or your SSD to request more data.
So bottom line, if I want efficiency, I should think sequentially. One direction.
Yeah, absolutely,
okay.
Absolutely. And that's especially important, we'll talk about it later when we talk about vector, is that modern hardware, you have enormous CPU caches. And if you're running sequentially through a memory array, very quickly, the processor notices what you're doing and starts to preload the next elements into your cache. So if you're going sequentially through a vector, you will absolutely tear through it phenomenally quickly, because
Is that the thing? Is that the optimization from the CPU, from the modern CPU?
yeah, exactly that. So you have these, level 1 cache, level 2 cache, level 3 sometimes, and it has this feature called I think it's preloading or something like that, where it notices what you're doing.
Isn't that part of the security vulnerability when they realize actually they went?
No, that's speculative execution, or well, there are several variants, weren't they? One of them is speculative execution, which I think is if you have an if statement and you have if this else that, then in some circumstances the CPU would try both instructions like in advance and then throw one of them away. But the throwing it away actually left some data in the cache that you could, if you were very clever, look at. But ask Oliver, he'd be happy to tell you all about how Spectre, etc. works. So input and output iterators are really awkward to work with. We don't like them very much, but sometimes we have to. Forward iterators are much nicer because we're allowed to dereference them more than once. So we can save a forward iterator and look back at it later. Bidirectional iterators are forward iterators, but they're forward iterators which also have an operation so we can step backwards through the container. So a standard list, for example, has bidirectional iterators because it's a doubly linked list, so the implementation contains a forward pointer and a back pointer, and we can step forward through the list. We can also step backwards through the list. And then the next step up from that, most powerful kind of iterators are random access iterators. And I've missed two important words off the end of this. We can step backwards or forwards arbitrary distances in constant time. That's 3 extra words. Because if we have a forward iterator, we can always step forward as far as we want, right up to the end of the container. But if we have to do that by stepping through each individual value, that's an order n operation, which we'll talk about very shortly. That's a linear time operation in the size of the container. Whereas for random access iterators, which are the kind of iterators the vector uses, for example, we can just move from here over to there in one step, in constant time. So if you think about raw pointers, they're random access iterators because we can just add a value to a pointer and we jump to that memory location, and it's a single CPU operation, it's constant time. There is a C++ 17, it added a 6th category called Contiguous Iterators, where it guarantees that your values are next to each other in memory. I haven't found out what the point of contiguous iterators is yet, because there doesn't seem to be any way to check that you have a contiguous iterator, and there doesn't seem to be any way to declare that your iterator is contiguous, so I don't really know what the point of it is. But for completeness, because it said so on CPP reference, I will mention there is technically a 6th category, although it doesn't seem to be very useful yet. So yeah, what I was saying last week, there are some algorithms, all the standard library algorithms specify what category of iterator they minimally require. So for example, standard sort only works on random access iterators. And if you know about how quicksort works, it sort of jumps around all over the place in the container, sorts things about. And that's only going to work efficiently if you've got random access. So there are a lot of algorithms that do only require input iterators, because all they do is run through, do an operation on every element, only need to dereference it once. There are quite a few more algorithms that operate on forward iterators. Yeah.
Just a question about STD sort.
Yeah.
So does that mean if you pass it on an iterator from an STD list, it will return an error during compile? Yeah.
It will return you a hideous error message with about 200 lines of like template debug horribleness, and it won't compile. That's correct. Yeah, one of the things, so I mentioned this idea of putting ranges in the standard library, and the idea of that is that we use a new feature called concepts to actually give you nice error messages. So in an ideal world, you'll try and sort a list, and it will just say, you can't do this because list is not a random access container. Fingers crossed we'll get that in C++ 20. It would make life a bit nicer because you wouldn't have to type .begin and .end everywhere, and you wouldn't have these awful C++ template mess that it's kind of infamous for. Some algorithms require certain category of iterators. There aren't many algorithms that require bidirectional. I think some of the partitioning ones. And there are a few, mostly sorting algorithms that require random access. And there are, I can't remember them off the top of my head, there are a few algorithms that do clever things where if you pass them random access iterators, so you pass them more capable iterators, you'll get a more efficient implementation. I can't remember them off the top of my head. Right, that was 2 slides on last week's material. So now you're an expert, Lauren. That's yeah. You didn't need 2 hours last week. You had 2 slides today. Yeah. Okay. Let's talk about algorithmic complexity. First of all, does everyone know what? Well, possibly not Lauren, because he was asking me to go over this. But to other people, do you roughly know sort of what big O notation means? Got a couple of nods.
What's the name?
Big O.
Kind of in past some of those.
Okay, well, hopefully you'll learn something. So this is a rough definition. The complexity of an algorithm refers to the resources you require to execute that algorithm, which is a bit like saying that relativity is about things going fast, right? This is not a very useful description.
Is it time or operations?
Well, we're mostly interested in time complexity. Space complexity is important for some problems. You know, if you've got huge data sets, if you're doing probably astronomical data or something like that, you're worried about how space efficient your algorithms can be. Most of the time we worry about time complexity. That's how long they take to execute. And algorithmic analysis is really complicated, really hard, really technical subject. I mean, people have PhDs in this. I don't know if you've heard of a guy called Donald Knuth. He's written this. How many? It's up to 6 volumes now of The Art of Computer Programming. It's pretty much.
And it's not finished.
And he's not finished. Yeah, the guy's in his 80s. I'm not sure he is going to finish it, to be honest. But yes, it's.
Also, trivia. Also, Bill Gates wrote his only paper on this kind of specifically on pancake sorting. I'm not exactly sure.
Oh right. Well, that I didn't know. So there you go.
And same for the creator of Futurama. Of course.
Yes. Yeah. There's an algorithm in an episode of Futurama.
Yeah, the one for the Globetrot, because I think I had a major in mathematics.
Yes. About everyone swaps their heads or something.
Yeah, he also did a paper on the same subject.
Oh, right.
Yeah.
Oh,
It's fascinating.
I didn't know that. So yes, we're sort of this is an immense subject, sort of PhD level stuff when you really get into it, and we're doing the equivalent of trying to explain relativity in 10 minutes. It's not going to happen, but if you know,
Relatively speaking,
we can just touch on the basics. This is backed up by some, you know, pretty high level maths. If you're really interested in it, any computer science textbook will give you a far more thorough grounding in the maths than I'm going to.
There is like a book which is this thick, you know, about algorithms.
Introduction to algorithm.
Yeah, it's like some kind of plant is on.
Yeah, exactly. Is the third edition is the one with the plant.
Yeah.
It's commonly called CLRS by the initial of for authors.
I remember that my tutor recommended that book, and he said like, okay, if you want to follow with the algorithms, here you go.
That is the kind of book which will push you to buy a Kindle. Otherwise, I think it's not manageable.
Otherwise, you get really big muscles carrying it around.
No, I mean, I used to read it when I was going around. If it was a paper version, would be a bit inconvenient.
Yeah.
Kindle is a little bit small.
You can zoom, I think. Yeah.
Get an iPad.
Yeah.
The size of the screen.
Yeah. Anyway, what I'm trying to say is this is the tiniest introduction. This is a very, very deep subject. So, big O notation. So most of the time, we're mostly interested in how an algorithm scales when we increase the problem size. So, if you give an algorithm, you call an algorithm a vector with 100 elements, and then you call it again on a vector with 100,000 elements, how is the runtime of this algorithm going to change? And this is expressed using what's called big O notation, literally because it uses a capital O. So this is very, very roughly, in terms, I have a maths degree and I hate myself for writing this. So given a mathematical, so this is not a C++ function, given a mathematical function f of n, its behavior as n increases is dominated by the fastest growing term. Right, so I've got an example on the next slide, which I'll go through on the board, but so if f of n was, you know, n squared plus 3n plus 9, then as we increased n towards infinity, this would grow as n squared, because n squared is the largest term, is the dominant term, it's the fastest growing. And you can define what fastest growing means very precisely using limits and things, fun things like that. And this behavior, this fastest growing term, is called the order of the function, and we denote it O of something.
There is also, if I remember correctly, omega of something and omega of something, which are
yes. Okay, so what I'm technically here, what I'm talking about, worst case complexity, is big O, and then the omega is the best case complexity. So for most algorithms, this doesn't matter, but particularly for sorting algorithms, the best case and the worst case can be quite different. Yeah. So the worst case might apply for some algorithms if you give it a set that is already sorted. So quicksort, for example, off the top of my head, I think is right. Quicksort is bad for already sorted lists. Yes. Why? So the worst case complexity, why? Mm-hmm. I cannot remember off the top of my head.
The basic answer is through more
yeah.
list.
I think because you do all the possible steps.
Yeah.
You don't stop.
Yeah. So, if you give an algorithm and n elements takes this many operations. So, n here, if we imagine we're talking about fundamental CPU operations, so things that the CPU can do in one go, like adding two numbers, multiplying two numbers, or division is a bit slower. But we make this assumption that basically all CPU operations are equal. And then the algorithmic analysis is about counting how many CPU operations you do. Again, this is so simplified that I'm almost afraid to be on the internet saying this stuff because somebody's going to pull me up on it and going, you're ridiculous.
We can skip that.
Yeah.
You can relate it to cognitive.
To what?
So when you say it's an operation, right, you do n operations, that's n number of cycles. If the CPU is running at 3 gigahertz, then say an add operation might cost 2 cycles. Then obviously if it's running at 3 gigahertz, it can do 3 gigahertz is what, 3 million operations in 1 second? Would it not be 3 gigahertz? So
yeah, but it's not that simple, is it? Because
so add operations 2 cycles, obviously it's that tiny. You can just divide, how many times is 2 going to 3 million, for example. It's not 3 million, 3 billion, isn't it? Sorry, gigahertz, billion.
Just a YouTube content. But what if it's multi-core CPU?
It still doesn't matter because it's still an add, for example, is still a single operation. You can't take a single add CPU instruction and make multiple cores run it. You have to pick a core and make a big operation.
But if you divide a lot of them,
then you can of course divide that up. Yes, if you've got 10 million add operations to do, then you can. But obviously the math is still straightforward because they're all going to run in parallel.
So unfortunately the people watching online can't do this. But let's say that for our particular algorithm, if we're operating on n elements, then it has 4n squared plus 3n plus 8 operations. And we say, okay, well how many operations is that if we got 10 elements? And it's 438.
You could rotate the camera,
I don't really want to touch their camera. Yeah. I'm going to change. So f of 100, some mental maths.
Is the same number with a 0 after each.
I think it's that.
It's 0. Okay, no. Go.
10 times.
Yeah.
Times 10 squared.
100 squared.
No, the first one, 4 times 10 squared. Plus
Yeah.
3 times 10.
Yeah.
Plus 8, plus, yeah.
Yeah. 1,000, so this is going to be 4 million and
2 zeros in the middle of each division. Yeah.
And we can carry on. Let's do 10,000, why not? Before the pen runs out. So 10,000, so we're going to get, I think, 400 million and 30,008. So this function is growing really quickly. So can you see that? Oh, I can move the ball in front of the camera in a second. So as we increase this, we're increasing this a step of 10 each time, and this is going up by a factor of 100 each time. Okay, to the point where, if we go a few more times, then all this bit, the 300, 3008, that's just noise. Right? That makes no difference. So if we went another step, you know, that's going to increase to 300,000. This is going to increase to 40 billion or something. So if we have this complexity, then really the only bit that matters is this n squared term. That's the fastest growing term. So we would say that this
Factor 100 every time.
has order n squared, because n squared is the dominant term. So the fastest growing term in this sequence is n squared. And we can demonstrate this. We're going up 10 every time, and our result is going up 100 every time. So that shows us it's an order n squared algorithm. And in this case, you can do that just by inspection. You just look at it and you see that n squared is the highest term. So as n grows very large, we're interested in the largest term here, which is n squared. So there's a bit of a maths lesson. In fact, there's almost no C++ to write at the end of this presentation, by the way. So as I just said, so this algorithm has order n squared, or big O n squared. Does that make sense to everybody? Yeah? So there are some common names for various orders of things. So if the algorithm operates in the same time regardless of how many elements you're operating on, we say that that's constant time. It's written O1. So that's the ideal. Like, constant time is what you want. Constant time is fantastic. But unfortunately, most real-world algorithms are not constant time. So if it's order n, then the algorithm, we say it operates in linear time, because if we double the number of elements, then we double our runtime. It's a linear algorithm. And we have some other ones. So O log n. So binary search, for example, is a log n algorithm. It grows with the logarithm of the number of elements.
Plus is sorting.
Sorry?
When you sort something in a language, usually.
Yeah. N squared is so log n is great. That's better than order n, right? Because log n grows more slowly, a lot more slowly than n. N squared, you probably don't want to be getting worse than quadratic time, but you can if it's n for k, for some k greater than 2. We say it has polynomial time, and then you get some terrible algorithms just running the exponential time. And there are various, you know, again, if you really get into this, there are all sorts of names for the different categories, but these are the common ones.
Just a question. The second one, is that log n or n log n?
This one?
Yeah.
This is just logarithmic time, but you can get n log n is very common as well. Yeah.
Is that log n logarithmic, or is it?
The base doesn't matter if that was what you're going to ask.
No, I don't know the base. But what's the common name for n log n?
N log n, I'm not sure, which is why I didn't put it on the slide. I've heard people call it linear rhythmic before, which I think is just a horrible made-up word. That's why I didn't.
I would just, like, humanist question.
Yeah.
Do I really have to understand that, or is it just the introduction, just to be aware?
Yes, it's good to be aware of it. I mean, you don't have to understand the maths behind it.
The impact is what matters.
Yeah.
Would O of 1 be a polynomial time?
O of 1 is polynomial, yes, for a trivial polynomial, yes. So if you really get into the computer science and P and NP and all that stuff, then an order 1 algorithm is.
If it's 1, then O
Can be
1 to the 1 is just constant time.
Yeah, but k could be 0 and therefore could be also polynomial.
Well, k0 to the power of 0.
Yes.
Yeah.
Yeah. So that's still polynomial time, yes. So even if this is like something hideous, even if this is n to the power 2000, as you grow, it's still, believe it or not, going to grow more slowly than 2 to the n. And we have this nice little graph that I nicked off Wikipedia that shows you how these different classes grow as we increase the problem size. So this is only going to 100. So you can imagine if this went up to 1 million or 10 million or whatever. So we see that order n grows linearly, it's a nice straight line. Constant time just goes along the bottom here, completely flat. Log n is great because it grows very slowly. This is increasing asymptotically, but increasing very, very slowly. Root n's also pretty good. And then this side of the curve, things start getting worse. So n log n, again, it's not too bad. So we want things to be as flat as possible. N log n, it looks bad here, but it's not too bad. But n squared, 2 to the n, and n factorial, I don't know of any n factorial algorithms, but
they would be horrible.
Yeah, they are impractical. In fact, encryption really relies on the fact that these algorithms are impractical to run on present non-quantum computers.
I think it's an algorithm when you compute all the, some algorithm in combinatorics with this kind of factorial.
Mm.
When
Do
you
you
get
mean Shor's
those
algorithm?
combination.
Do you mean Shor's algorithm? Shor's algorithm. It runs on quantum computers. You're not thinking that.
No, just combinatorics. I give you
there's a general something sieve that can sieve to factor prime numbers, factor RSA keys. But again, that's traditional.
No, I mean like I give you 10 elements, so you show me all the combination what you can achieve with the n elements and so on.
Probably be n squared, I would think, just off the top of my
All
head.
the combination of all length.
Oh, well, no, that.
No, not of all the combination.
Not all
of
pairs?
Yeah, all of it, yeah.
Oh.
That's what we like
Yeah,
all
I-
the combination of n plus all the combination of n and minus 1 elements and so on.
Yes, I can't do that in my head.
Factorial is the one which grows the most, right? And nothing happens alone.
Yes.
Okay.
What do you mean by asymptotic?
Asymptotic, it approaches but never actually reaches some value. So it's a maths thing. So it's a as I say, as n tends towards infinity, it gets closer and closer and closer to some upper limit, but it never quite reaches it.
Just a question?
Yeah.
I mean, the fastest sorting algorithms are always n log n.
Unless there are special conditions.
Yeah. Yes. Well, it's got to be at least order n, right? Because if all you're doing is looking through to make sure the container is sorted, then that's still going to take you order n.
Yeah.
So, but yes, order n log n is what you. But I think there are some that run in, n log n best case, but they have worst case performance. Their worst case would be quadratic. So. So we want to be this side of the curve, if we can. And if we have to go this side, we don't want to be getting too steep, is what we're saying. Big O is important. It's probably, if you look at nothing else, when deciding whether to use a particular algorithm, theoretical complexity, big O, it's important. And in the standard library, every single algorithm will tell you its complexity. And not only that, every operation on a container will tell you the algorithmic complexity. And big O is important, but it's not everything. Because if we say this is order n squared, well, we've only got a small number of elements. These lower terms are actually still relevant. Right, if we only had 5 elements, that would be, well, I can't do it in my head, but these terms would be much more important. So in terms of real-world problem sizes, you can have an algorithm that is, in terms of its big O, is more efficient, but when you look at real-world problem sizes, that more efficient algorithm comes with a huge constant factor, which means that in sort of performance terms on an actual computer that you're going to run, it might actually do worse than something that is theoretically less efficient.
And a good example of that would be, say you had an unordered set of integers and you had 5 elements. then the complexity of an unordered set is obviously O1. But let's say a stood vector, searching for it is a complexity of On, so it's a linear complexity, so obviously you've got to just keep going until you find it. The thing is that in an unordered set, you've got to compute a hash, so it's obviously constant all the time, but that amount of time that it takes to compute the hash is going to be longer than it takes your CPU to just look through all 5 elements. So a good example is that linear time can still be faster than constant time because that constant time is just bigger than the total amount of time it takes to look through a vector.
Yeah. So particularly we're talking about cache level 1, cache level 2 cache. CPU caching means that, as Ollie was saying, if you can just go through a set of memory locations very quickly, you can get tremendous boosts from your CPU that really distort this theoretical complexity. So theoretical complexity really comes into play when you're dealing with huge data sets. But for most kind of practical problems, you're not necessarily dealing with tens of billions of elements in a set.
What happens if you start with a small set, then but you want it to allow the system to be scalable to...
Well, then you've got to really look at this carefully, yeah.
So you use 2 different algorithms?
You may choose to, yes. And I believe standard sort, some implementations of standard sort do that. They look at your problem size and they will dispatch to a different sorting algorithm depending on how many elements you're talking about. Because even something like a bubble sort is fine if you're only sorting 5 elements.
Similarly, you write a class that starts out with a stood vector, and then once you cross some threshold, you say, all right, we'll stop using the vector and start using an unordered set, unordered map, whatever.
Yeah.
You've got to write that, obviously.
Yeah, and modern CPUs have all these, out of order execution, pipelining, and things that can really distort things. So you don't necessarily get the theoretical complexity that you might expect. When in doubt, measure, profile your code, try different things out, see what's fastest for your typical data sizes. This is just great advice for anything where performance is concerned.
Yeah.
Don't just assume, never assume, measure. Okay, now that was it. That was my half hour on algorithmic complexity. So there you go. You asked for that months ago, and here it is. Why am I talking about this today? Is because everything in the STL is not defined exactly. It doesn't. The C++ standard doesn't say precisely what an implementation should do. What it does is it says it should perform these actions within this maximum complexity. So, for example, standard vectors, the square brackets operator, the element access operator, the standard says this must operate in constant time. And standard sort must have O(n) log n worst case complexity, actually, which rules out certain sort algorithms.
So implementation changes according to what compiler I use, or?
Yeah, it can do.
Okay.
Possibly, yeah.
And what standard library your compiler uses.
Yeah.
Okay.
Clang can compile against GCCs or its own.
Okay. So for example, with CMake or the like, I could fine tune and decide, okay, user.
Well, yeah.
This is always going, I don't know, to be a small vector, so please use this kind of sorting.
No, you can't get that level of granularity,
okay.
Not with the standard library. I think Boost has a variety of sorting algorithms that will perform. This algorithm might perform better for a data set with particular properties, or you could choose a different algorithm that performs better for other properties. Again, said it on the last slide, always measure.
So, what about the sorting algorithm that uses bubble sort for small data sets and quick sort for large data sets? It won't meet that complexity requirement.
That is true. You might argue that if it's only using bubble sort sort of up to, let's say, 10 elements, then that's actually sort of constant time, where the constant is the maximum time for 10 elements. Okay. And if it operates in constant time, then that's well within this limit. Although that's really me stretching the definition, because, yeah. That's a good question.
I think the most hybrid implementation of fundamental sort merge and quicksort, according to the site.
Yeah.
I think.
Yeah, I think so. All right, so that was complexity. Very, very, very brief introduction to it. Basically, it's all to do with how things scale, and we want the smallest value in there that we can have. Smaller is better. So let's go on to talk about the standard containers. I thought there were 2 categories, but according to CPP reference, there are 4 categories of containers. And the first, the most common, the ones you probably use most often, sequence containers. These are ones where the elements are stored in the order you put them into the container. Okay, so when you iterate over them, you get them in the order that you added them.
A vector.
A vector is the prime example of a sequence container. There are a few others that we'll get to in a second. The second category is associative containers. So these are ones where the elements are sorted within the set, within the container. So set is actually an example of an associative container, so is standard map.
An ordered map?
An ordered map, yes. Okay. So they're ordered according to, by default, by the less than operator.
Okay.
Unordered or just map? Unordered map or just map?
This is map.
Just map?
Yeah.
There's no ordered map, it's just ordered map.
Yeah, but it is, in practical terms, an ordered map. And we have unordered associative containers, and these are the ones that are hash maps, hash sets. So these do the same thing, but they have slightly different complexity guarantees. And then finally, finally we have container adapters that are not really very heavily used in my experience, but they exist, they're there, so I may as well point them out.
Do you know any example
of container adapters?
Yeah.
Yeah, I've got a slide at the end. I'll tell you what they are.
Don't use a heap.
Sorry?
Don't use a heap.
A heap? Yeah. There is a heap adapter, yes. Or max heap, I think we call it. But I haven't actually used it, but yes. So we talked last week about the iterator concept, which is this sort of, it's defined in the standard that tells you what a type must be, what must do, what member functions it must have in order to meet the requirements of an iterator. And there's another concept called container. And in order to meet the requirements of being a container, there are certain requirements on a type. One is that it has certain member type defs. So there's a value type, which is what you get when you dereference an iterator. There are guaranteed to be 2 nested types called iterator and const-iterator. And whichever type this refers to, you're guaranteed that that will meet the requirements of the iterator concept. So this is the sort of generic programming aspect to it. So rather than, if you're doing Java or something, you'd have like a container base class that everything then inherits from. With generic algorithms, things are done slightly differently. It's what's called duck typing. So we abstractly say it must meet these requirements in order for you to be able to instantiate a template, one of the function templates, the standard library, the standard algorithm function templates with these arguments. It must meet the container requirements, or it must meet the iterator requirements. In particular, for containers, iterator and const-iterator will usually not be the same type. So, if you recall from last week, the plain iterator is the one that lets you modify the elements of the set. So you could, for a vector, you could say like star iter equals 4, for example. Whereas a const-iterator only provides read-only access to the container. And as I say, they're usually not the same type, but you're guaranteed that you'll be able to convert an iterator into a const-iterator. And you can also compare them for equality, iterators and const-iterators. So if you call begin and end on a non-const instance of a container, you'll get a mutable iterator. And if you call begin and end on a const instance of a container, you'll get a const iterator.
What's the const on?
Right, this is where we went into this last week. So you should have turned up. But the const refers to the element that it's pointing to. So this const underscore iterator means the thing it's pointing to is const, not the iterator itself.
How do you get the const iterator const?
You can have a const iterator which is itself immutable. It's not very useful, but you can have one. Right, because it would mean that you wouldn't be able to mutate the iterator to point to a different element. So I think it's probably before you started coming to these classes, but we talked a lot about the difference between a const pointer and a pointer to const, for which the C++ syntax is horrible. But it's exactly the same difference with iterators. You can have an iterator to something that is const, and we call that, really annoyingly, a const underscore iterator. And you can have an iterator that is itself immutable. Is this making sense? Yeah, okay. I just finally note that all the containers have this extra template parameter called an allocator. It defaults to a class called standard allocator. And if you're really doing advanced things, you can use that to customize how the containers allocate them, where they obtain their memory from. So this is pretty advanced stuff. You know, if you're trying to eke out absolute maximum performance, if you're writing a AAA game for a PlayStation 4 or something, you'd want to use custom allocators. I think it's rare in sort of general code, but I'll just put it there as a...
The typical reasons range from wanting to over-align memory. So the standard allocation may say, oh, I'll align it to, say just whatever the CPU architecture is, say an 8-byte boundary, it might be size good enough. You decide that I want to align it to a page, which I can say 4 kilobytes. So you can use it for over-alignment. You can also use it for, say, over-provisioning. So you might say that I'm going to actually, I know that all my code actually will eventually grow to fill up the container with quite a lot of data. So whenever it calls the allocator, I'm going to sort of defensively give it much more than it needs because I've got loads of memory to play with. Or you can go the opposite direction and say I'm just going to make sure you use an absolute bare minimum. So again, it's a very specialised use case.
Stack allocators as well.
Yeah, allocator, yeah.
Yes?
I read somewhere that they don't get as used as in, when you use them, they don't get used in the way you think they expect them to be used.
Yeah, but standard maybe.
I don't know about that.
Like if you, let's go, I can't think of an example, but I think the point I'm trying to get at is if you have a container, all of its bookkeeping will not be using the allocator.
It will be using the allocator. So every time it needs to allocate new memory or construct or destroy an element, all of those functions happen via the allocator.
Okay.
Well, the structure may not. If it needs more memory, it has to go to you. If it doesn't need more memory, it's going to you because it may not go to you.
But it was an article, it was an item in one of the Myers books. I can't remember.
Okay. Well, I'm going to defer to Scott Myers, obviously. So.
But it was for C++
Yeah.
2003. So.
Yes. So yes. Okay. So allocator, the allocator interface in C++ 2003 was really horrible, and they changed the way it works a bit. They put a proxy class called allocator traits in C++ 11 that made things quite a bit nicer. Made it much easier to implement your own allocators if you need to, which I've never really come across a use case, but I'm told that if you're doing very high performance C++, you really, this allocator thing is brilliant.
High performance means?
So, for example, AAA games or high frequency trading or things where microseconds matter.
Pomodoro.
Yeah, absolutely, yeah.
Precise.
No, I mean it's sort of a case of are the extra costs worth the benefit that you get? from
and
it.
then create like a Pomodoro, which is for high performance.
They do have, you know, microsecond resolution timers that fire off an event with, as I say, microsecond resolution.
And you're talking about real-time operating systems and...
Yeah. Then you've got to negotiate with the kernel to make sure you haven't been, you know, suspended. Your thread hasn't been suspended.
How much harder would be to create as a project for fun? Yes, like Pomodoro with such frequency.
We could do stuff with high-resolution timers, and if we ran it on a multi-core system and gave it real-time access, we could do this kind of stuff. But I mean, you know,
I think as a learning exercise, there are more practical things we could do.
So it wouldn't be like.
I mean, writing a custom allocator class might be an interesting exercise to write a stack allocator, for example. But actually doing the HFT stuff, I think, is probably beyond my ability to teach people to do.
I mean, in terms of usefulness, I think that getting even contemplating getting onto doing custom allocators is something you only going to bother ever getting into when your level of knowledge of C++ is completely and utterly fluent. And if it's not, then it's just you're trying to run before you can walk.
Yeah. I really put this little bullet point on the end just to say, if you go to CPP reference and you see this allocator parameter and you wonder what it is, it's to do with, you can customize it to customize the way that this container obtains memory. So the default allocator just calls new and delete, which is fine for the overwhelming, 99.9% of cases.
When you mentioned the extra cost of using Allocator, you mean the extra development cost or the performance cost in terms of overhead?
Oh, sorry.
You mentioned we need to verify if extra cost is worth the gain on this allocator.
Yeah.
You mean cost in terms of...
Cost in terms of development time?
Yeah.
Yeah.
Okay, sure.
Would you use it if you're talking to hardware?
Custom allocator, possibly, not necessarily talking to hardware, but say potentially running on a system with no operating, on bare metal.
Yeah. So you get like embedded operating systems that have no free store, they have no heap. So you can't use new and delete. So you wouldn't be able to use standard vector with the default allocator. But you could write a stack allocator for that and still be able to have a vector and still be able to use the algorithms. That's just off the top of my head. Yes. So let's talk about sequence containers. These are the sequence containers that the standard library gives you. So we talked about standard array before. It's basically a wrapper around a raw C array that gives it a nicer API, turns it into something that matches this container protocols, container concept. There's vector, which you should use for everything. Standard list, we mentioned it's a doubly linked list. This is a new one was added in C++11, forward list, which is only a singly linked list. There's something called standard deck, which is a double-ended queue, which we'll talk a little bit more about in a minute. And then finally the standard string, which is pretty much, it's the same as a vector, except that it has two other things. It has a small string optimization, so it doesn't allocate if you're within, if you only have a small string of a few characters. And secondly, it has this specialized API for dealing with strings. But performance-wise, it's pretty much identical to a vector.
Also notice the GCC used to implement doing strings copy on write, which
well, that's long gone. So.
Not supposed to do, and it's not gone now. As long as you're using a modern compiler and...
It was fine to do C++ 98, by the way. The standard said that was fine.
True, yeah.
So standard vector, you all know about standard vector because you've all used it. It's a dynamically sized random access array. So I said the standard tells you what the complexity of everything, of all the operations are. So for a vector, one more. Element access is in constant time. That means we can get to any element in the vector it's an order 1 operation, constant time operation. whether you want to access element 0 or element 10 billion. That takes the same amount of time. Adding elements to the end of the vector is amortized constant time. Now what does this mean? It means if you do it enough, it looks like it's constant time, basically. So if you think about how a vector works, you add elements to the back, eventually you run out of capacity, and it has to go to the operating system and say, give me more memory. And it asks for a lot more memory than it needs, probably. So the standard implementations will generally double the size of the vector. Every time it runs out of memory, it will double what it's got. That's called the scale factor. So libc C++ actually uses a different scale factor, but the classic implementation uses a scale factor of 2. So every time the vector runs out of space, it requests twice as much memory as it had before.
And I'm guessing there is no smarter way of dealing with that.
Yeah, reserves.
Yeah, there's a member function.
No, but in a sense, like you reserve, like you take twice the size. For example, if I have 2 elements, I got 4. If I got 4 elements, it goes to 8. Yes?
No, yeah.
But isn't that like a smarter way of dealing with like vector type?
Well, there's no standard library to cyclically know how much you're going to fit it with.
Yeah.
So the answer is that there's a member function on stood vector called reserve, and if you
reserves how much
it tells it how much you're going to use. Yeah.
But my question was basically whether it's like super clever magical thing that works in a better way, not like vector. So you have, let's say, like a problem when the vector needs to relocate to the new bigger space. So is it like some very brainy person come out with a super new vector thingy? It's not. We're not close to anything like it.
One in Dublin usually is considered the smartest for a general approach. If you know, for example, your vector doesn't grow much sequentially, you can write your own, which increases 50% each time, something like that.
So typically, so I've got a vector of 10 elements, right? And then I want to add, I don't know, 10 more. Then I've run out of space. So there's obviously 2 ways that this can be addressed. Generally speaking, what you can expect is that you're going to end up allocating a completely separate area of memory with space for the existing and space for the new. All of the stuff inside the old is going to get moved over here. So if it's actual classes, they'll get stood moved, so their memory. There's still a memory copy going on, but it obviously might be a bit cheaper if it's holding vectors and stuff, because then what's got a copy is pointers rather than actual objects. But then the point is that that memory will go over here and define a name with empty space, where you can use it. Obviously, alternative option may be possible. But I believe the standard library, any standard libraries give you this one, is that it can say, okay, well I've got this chunk memory, see if the operating system can just keep this here and then maybe let me go further up. And if you can achieve something like that, then obviously that makes it incredibly cheap. Also, it's a reason for using allocators. You could use a custom allocator like gemalloc, where it would say,
I think Folly's FB vector.
Yeah.
So Facebook had this open source library called Folly, which is full of very useful stuff, including a vector that lets you sort of customize its behavior, uses realloc.
Also, source engine C-util vector should do the same.
Okay, well, if you're into games programming like Justin, then you can go dig into the source engine. I'm sure Unreal has a similar thing, and so adding elements to the end of the vector is amortized constant time, right? So if we're within the capacity, then it's really quick. All we have to do is construct a new element or move it into place, depending on which overload we call. Sometimes we're going to run out of space and we have to say to the operating system, please can I have some more? And that's going to take a lot longer, but still overall this is going to be constant time. But adding elements anywhere other than the end is linear in the number of elements already in the vector. It's order n. So if we think about, we'll go back to this thing, vector diagram here. If we want to shove elements on the end, it's really easy. We just move this end sentinel further away, put the stuff the elements in there. If we want to add something at the beginning, what we've got to do is we need to copy or move all of these elements one place down. And the length of time that takes depends on how many elements we already have. So insertion anywhere but the end is an order n operation for vector.
Also, one thing to probably note is this amortized constant time, but don't take that too lightly. If you try adding 1,000,000 elements to a vector and you just construct it and then go in a loop to add them, try timing it versus telling it, please reserve 1,000,000, and then do it, you'll discover it's way faster when you just tell it how much you're going to use compared to just filling it up, because it causes so many reallocations.
Yeah, Bjarne saw a talk where he said he's stopped using reserve because he found it just, in practical programs, it didn't make a difference. Yeah, so in micro benchmarks you can see the difference, but according to him it's more trouble than it's worth. But
Surely not large. Like, if it's like 10 elements, probably not, but if it's like millions, I'm sure.
And iterators, we mentioned this last week, iterators are random access for vectors. In fact, they're contiguous, which is this silly new category that I think is pointless in C++ 17. Why am I telling you all this? It's because standard vector should be your default go-to container for pretty much everything you do. Repeat it once again, caches on modern CPUs mean that running through memory locations in order is super duper fast, and if you can use a vector for your problem, use it. When in doubt, use vector. This is probably the most important sentence that I'm telling you today. When in doubt, use vector. This is slightly facetious, right? If you can't use vector, think about how to change your data structure so that you can. It really does make that much of a difference.
Would you use a vector, so even if you have a problem like, okay, I needed to take this input each day of the week, so it cannot be more than 7 elements. Would you use an array or still a vector?
I use an array.
Okay, so standard array. You could think of standard array as a sort of an optimization of a vector, where if you know that it's...
I would think more the other way around.
Or perhaps vector is a generalization of an array, then, if you prefer the other way around. So, yeah, start off with vector, but if you know the maximum size and you're happy with step allocation, use an array instead.
Okay.
I wouldn't say that. I mean, vector's obviously on the heap, so you can move it around. Obviously, like having a stood array, because it's on the stack, means that its move semantics are almost meaningless. Using a class state is what we move. But having an array of primitive types moving does nothing, you just copy and stuff.
Yeah.
So, I mean, they're just two different things, really.
So your preference would be?
As a use case. I mean, if you're saying that I
think if you've got a small number of things that you know you only ever need these many things, because yes, the semantics of array are a bit different as well, in that vector can grow and an array can't.
Yeah.
So array has a limited number of use cases, and if you fall within those use cases, then try it and see if it's better. When in doubt, use vector though.
Do you have to initialize the standard array?
Yes, in fact, it's got a fixed size, and all the elements get default get constructed at the time that you first create the array.
You can give it an initializer list, so you can give the thing an initializer list so that it will obviously in place construct whatever things it's going to hold, but it will have every single element initialized by hook or by crook.
Yeah. So if you have an array of 10,000 ints, all of those ints are going to be, I believe anyway, default initialized to 0, I think.
But can they just merely measure the size of the type and create the exact size per element?
That's exactly what an array does. Yeah.
Okay, but when you said it calls the constructor.
Yeah, if it's a type with a real constructor, but in the case of say ints, they're just default initialized to 0.
So when it calls the constructor even if you haven't assigned anything to it?
Because that's the whole point, it's constant size.
Yeah.
So because the array is constant size, it's going to hold 5 objects. So that also means that, for example, if you have an array of some class that does not have a default constructor, it will not compile until you provide something for each element to construct with.
So when you were making an example, I could allocate extra space in memory and say you could use an array for that?
Yeah, as long as you know exactly how many you want. It's exactly what you need.
The maximum ideally. If I want to repeat it.
As long as those objects are either default constructible or you don't mind constructing the extra crap, yeah.
Okay.
So if you needed, let's say you had a to-do list for each day of the week. Well, you know there are only ever 7 days of the week. 7's a nice small number. You're going to want your to-do list for each day of the week. You might think about using an array there, just because it's a small number of things, it's a fixed number of things.
Do I get some small boost in performances?
Potentially, because you're not, so vector allocates things on the heap and array uses the stack. So basically, any problem for which you could use an array, you could also use a vector. In some cases, array might be more efficient. When in doubt, measure. That's the other important takeaway from today.
And does the vector require default construction?
No. It used to, but it doesn't after C++11. Standard list. I'm really telling you about standard list to try and discourage you from using it. So for a vector, adding at the end was constant time, amortized constant time. For a list, adding an element anywhere in the list is constant time, which is brilliant, right? You can insert things in the middle and you just have to change a couple of pointer values, it's constant time. But the price you pay for that is that accessing a particular element is linear, it's order n, linear in the number of elements in the list. Or accessing an arbitrary element, I should probably say. Standard list, they added this thing in C++11 that they have this size member that's guaranteed constant time. Standard list has bidirectional iterators. It's a doubly linked list. There's also standard forward list that is slightly smaller. That uses slightly less memory because the nodes only have a forward pointer and it only has forward iterators. I've never used forward list for anything, so I'm sure it's there for a reason. People must have wanted it, but yeah.
For interviews.
Well, possibly, yeah. Yeah. Standard list is technically, all right, so there is a node-based container concept. The list doesn't actually implement it, but basically what happens is when you add a new element to a list, it needs to go away and allocate space, allocate storage on the heap for this new element. So whilst adding an element in the middle is constant time, part of that constant time is going away to the operating system and saying, please can I have some memory for this new node? And that's really slow. All right, so this is exactly what I was saying by big O isn't everything. So although this is, in theoretical terms, a constant time operation, in practical terms, unless you have a really, really, really big list, this constant factor, the constant factor of calling new to get new memory from the operating system is going to dominate your runtime. So the guideline, prefer a list to a vector only when frequently inserting or removing elements from the middle of a really large sequence.
Or if memory fragmentation is an issue. Like if you're going to have a list of a really large number of objects to the point where you're saying, I might make this computer run out of memory. Now, if you were to use a stood vector, imagine that your computer's memory was a length of putty, right? So the operating system will give you a little piece of that putty to use, but the string is always going to be this fixed amount, right? So if I get some putty back by the program says I'm done with it, you can reinsert, it gets reinserted into the empty gap where it was. But as the OS keeps handing out little chunks, you're going to have less and less contiguous spaces of memory. So for example, if I ask for a vector, if I have a vector and I ask for 4 gigs of memory, and maybe my computer's got 6 gigs, and actually, technically speaking, there is the amount of free memory that Task Manager showed you is actually slightly more than your vector's asking for. That's meaningless because you need a continuous amount. You can't a vector must be start to finish a whole lot. Yeah. Whereas a stood list doesn't have to be. It'll just get little pieces here and there and then just make them point to each other. So one use case for a stood list is when you're going to like it says there, use large amounts of data, memory.
But with a very long double linked list, I will not increase the proportionally override in previous and next on each node.
You want what, sorry?
I would not increase the memory that I require in terms of overhead having previous and next on each.
So you've obviously got the point, you've got the overhead of the pointers, because say on a 64-bit system you're now spending 16 bytes on the pointer to previous and the pointer to next. So that's also an argument where you might want to have a forward list, because you can save 1 pointer's worth of data because you can't go backwards, but you can go forwards.
Anyway, but usually it's more memory than a vector.
Yes, so for a given number of elements, a list will occupy more memory.
So in the case that you was making, when I have a very long list, linked list might be still too bad, because if they're running out of memory, maybe that is still can clog.
Yeah. I was really talking about fragmentation, so for really long-lived processes.
It's not about having, like, not physically having enough memory, it's not physically having enough contiguous memory. If you've got loads and loads of free memory, but there's all these little chunks taken out of it everywhere, then the vector's going to be what the list is.
So,
is there any way for me to defragment it once I have a program which is?
Yeah, the best strategy is to use your own allocator. Firefox does this, they use gemalloc. There's a few popular memory allocators, and using them is generally as simple as linking to them. So you don't actually have to physically write any code, you just build the library, link to it, and you get it. Gemalloc, tcmalloc, there's a third one that's getting popular, which I completely forgot the name of, but there's benchmarks and stuff. But yeah, carry on.
So really, there's similar advice to array. So we were saying, start off using vector, and for certain situation, an array might be better. Again, start off using vector as your default sequence container, and there may be certain situations, certain limited situations where list is better, but definitely don't reach for a list first, reach for a vector first. In Dec, why am I mentioning Dec? Because it's got very similar properties to a vector. Element access is constant time, same as vector. Insertion and removal at the end is constant time, like a vector. Insertion and removal anywhere else is linear in the size of the container. Iterators are random access. It's also got this extra property that adding an element at the beginning is also a constant time operation.
So why not using them?
That's a very good question. Yeah. This looks better than a vector, doesn't it? Because it's giving you the vector guarantees plus an extra one. Sounds great. Why don't you use it all the time? Unfortunately, this is the drawback to just looking at things in big O terms. Dec has a much higher overhead on operations. So for start, it has a much higher overhead on memory use, but also in terms of accessing, there's going to be an extra indirection every time you try and look at an element. Their amortized complexity, their complexity is worst case the same, but in practice you're going to find it's slower than a vector. If you just use it as drop-in replacement for a vector, you're going to find your code getting slower. So again, Dec is a special case container for when you're frequently adding things at the beginning.
It's also basically a set of chunks. So if you internally, you can imagine it as a set of internal vectors.
Yeah.
So you're also not going to get as good cache locality, so if you just use a vector, it's all contiguous.
Yes.
Whereas in Dec it's fine.
But in terms of implementation, how does it work when I add something? It is if it is the second half, it works like a vector. If it is the first half, instead of shift everything to the left, or always to the right.
So imagine it like almost like a vector of vectors, right? So when you add something to the beginning, that's really quick because it's full of fixed size chunks.
Yeah.
And this chunk is very small, so when you add something to the beginning, it's not much bother to move things. And when you add things to the end, you're just popping it on the end of a vector, that's the same. And when you want to address an arbitrary element in the middle, it's still constant time, but first you have to work out which of these chunks you're in, and then you have to get the offset into that chunk. So it's still a constant time operation, but it's having to do more work than just calculating the offset, which is what vectors.
The chunk needs to be of the same size?
The chunks are the same size, yes.
So if I add too many things in the same chunk, it is going to shift?
Yes.
You want to just create a new chunk?
It does, yeah.
So basically, it's basically like, imagine a T star star, right? So you'll try this template on, and internally it's going to be like a T star star. So you're going to do one point of dereference, get to the block of them, so to get to the next level, and then somewhere in that next level will be what you want. So it's just like a 2D array almost.
So once again, start off with a vector, use a deck in special circumstances. If you're frequently inserting at the beginning and the end of a list of a vector, then you might find you get better performance with a deck.
It's always keeping the order, right?
Yes, yeah, so all the sequence containers maintain things in the order that you insert them.
Okay.
I didn't add string. I've said use vector for everything. String is fine if you're dealing with, well, strings, that's what it's for, right? And it gives you the same performance profile as a vector, so string is the one to use if you're dealing with text. Associative containers, these are the ordered associative containers. There are 4 of them. There's map, set, multi-map, and multi-set. I'm going a bit quicker because we're running out of time, weirdly.
Okay, still almost an hour.
Yeah, but you've got work to do as well. Standard map is a sorted container of unique key-value pairs. So if you're familiar with Python's dictionary type, or an object in JavaScript, that's a hash table actually, but it's a key-value storage. Right, so key-value storage, standard map. And a standard map keeps its elements sorted according to the key. So it looks at the key, it tries to find out where this key would go in the sorted order.
So what's the difference between std map and std pair? Am I correct?
So, okay, so internally,
Yeah.
internally a map stores a standard pair of key value.
Okay.
Yeah.
Pair is an element. The std map contains n number of pairs.
Oh, okay.
Yeah. So map's value type is actually a standard pair.
Oh. Thank you.
So because it's a sorted container, element access and insertion is O log n. Uses the binary search algorithm, which is log n. So that's really quick. Insertion anywhere is log n. That's great. Iterators are bidirectional. It's sorted. We can move forward and backwards, but we can't move an arbitrary amount in constant time. We can move an arbitrary amount in logarithmic time, I suppose. Iteration order is well defined. If you take a map and you add some things that sort later, you're still going to get things in the sorted order. It's typically implemented as a red-black tree. Again, the standard text doesn't tell you how to do this. It just tells you how it should behave, tells you what the complexity guarantees must be, and that basically points implementers to this thing called red-black tree, which you can read all about on Wikipedia if you are really interested. The default is to sort elements using operator less than. It means that if you put your own elements, your own data type in a map, you need to define what less than means for your element. Or you can customize it. It has a template parameter called compare. You can give it a custom comparator. And some possibly contentious advice that standard map should be your default go-to associative array type. So if you just need a linear array type, a sequence, use vector. Map is probably the better default for an associative array. No, I was wondering whether Ollie was going to pick me up on that.
An ordered map?
Sorry?
An ordered map instead of...
Rather than a hash map. Yeah, it's this is Strauss-Strup's advice, and I'm not going to argue with him. So he knows what he's talking about. So there's also standard sets, which is a sort of container of unique values. You can think of it as basically like a map, but only with keys. I should have worded this differently. Think of a set as like a map with only keys in it. A standard set is quite useful if you want to make sure that your elements are unique. Because if you try adding something to a set that's already in there, it will say, no, I can't do that. We've already got that element.
You get an error? Or you just get the same set?
Well, it depends which particular member function you call.
Okay.
Yeah. However, you can often, because set is a node-based container, it has to allocate for every element you put in it, you can often achieve better performance by using a vector and keeping it sorted yourself. And keep it, and checking uniqueness yourself. This isn't a hard and fast rule, but when in doubt, use vector. Have I drummed that into you enough yet, by the way? When in doubt, use vector.
The last statement, I mean, if you have a large vector, you have to go through quite a lot.
Yes, exactly.
Right.
So if we're talking really, really big values, then the algorithmic complexity, the big O, is going to come into it. If you've got a set with 10 billion things in it, and you want to make sure they're unique, then set is a good container. If you've only got 100, you may well find that vector gives you better performance.
Do you remember many chance the deletion is constant or what instead?
For what, sir?
Deletion.
Deletion will be log n, because it has to go and find the place to delete the element from.
And rebalance the tree afterwards.
Yeah. Those are the ordered associative containers. Oh yes, and there's also multi-set and multi-map, which allow you to have two values with the same key. Which?
Well, you could just have whenever I think of doing that, when I wanted multiple values, I always think, why don't I just have an unordered map with whatever key I'm going to use, and then have a vector of values. Like I do frequently do that. Like it's got its uses, but depends what you want to do.
I don't get the multi-set because you say it's like having multiple keys of the same value, but you don't get values in set. It's all multi-set, or does it work?
Multi-set allows you to have multiple keys.
I mean, there's only keys, right?
Yeah. So if you think of a multi-map, it lets you have two keys with different values attached to them.
Or one key returns off.
I think the find method actually returns you the first. Anyway, whatever.
Yeah.
Multi-set. In a multi-set, the keys aren't unique. So you could have a multi-set that contains 2, 2, 2, 2, 2, 2, 2.
What is the use case? What is the advantage?
What's the use case? I don't know. I was trying to think of a good use case for a multi-set. I can't, but I'm sure they exist.
Probably.
C++11 added these unordered associative containers. They're the same, but they have this horrible unordered thing at the front. They really should have been called hash map and hash set. I don't know why they weren't, frankly.
Did it mandate using a hash?
Yes, it's got a template parameter called hash, and it uses standard hash by default.
I
I do actually know the reason. It's because Microsoft had, as an extension, implemented classes called standard hash map, and they didn't want to clash with Microsoft's extension, so they used this ugly thing called unordered map.
That's how we never shared time with mutex as well.
It was also, I think, something at the Ash, it was called Ash or Ash map, I remember was problematic, was not so good in performances. Maybe the implementation, so.
Quite possibly. I mean, other people do complain about standard unordered maps performance as well. But let's start again. So, unordered map is basically what a hash table is in other languages. Element access is order 1 on average and order n worst case. So, won't delve into it too much, but a hash table is made up of buckets. You apply the hash function to find out which bucket you need to put your value into, and then each bucket itself is pretty much implemented as a linked list. So once you've found the bucket, if this bucket has multiple things in it, you have to count your way through that list. And the worst case, the terrible case, is if your hash function returns the same value for all the things you put in. Yeah. So for an ordered map, this was guaranteed O log n. For an unordered map, it's better on average. Worst case is much worse.
But it's not also so likely.
It depends on your hash function. Yeah.
Yeah, okay, but it would be something I would write a paper about if I get something for which everything goes in the same bucket.
Yeah.
So common.
Yeah. And the other thing is about these constant factors. Again, coming up, the fact that big O isn't everything, is that computing a hash can be quite an expensive thing to do. Whereas just comparing keys using less than should be a very fast thing to do. Probably cheaper than computing the hash. So, again, it's order 1 on average, but that doesn't tell you everything. What you can probably say is that for extremely large sets, it's going to be quicker. Extremely large maps. So keys are compared using standard hash, which is defined for all the built-in types and most of the standard library types. If you want to put your own types in an unordered map, you have to write a specialization of this standard hash class, which is a bit of a pain, and it's easier to write your own implementation of less than, which is one of the reasons to prefer map.
Isn't the standard the hash implementation just a class with an operator parentheses?
Yes.
Yeah.
It's just a function object.
So,
sorry.
Could you not just have a 2-string operator for your class type and then use a string after the string?
Well, you could. That might actually make it even start.
Yeah. Well, because then you're going to have to allocate a string, aren't you? Yeah. I mean, it's a legitimate approach, but it's not necessarily an optimal one. So, as with all the hash table, performance is highly dependent on the quality of the hash function, and for cryptographic purposes, this is really, really important. Or for Python got in trouble because their hash function was quite predictable, and people started deliberately generating hash collisions, which meant it was getting linear time all the time, and they were causing denial of service operations on servers by deliberately giving it data that would cause hash collisions. So the hash function is really important. There is this standard one. There's a template parameter, so you can supply your own hash function if you need to. Were you going to say something?
Yeah, I was going to say, so I don't know actually what libgcc, GCC, C++ map library uses. I do know that in Clangs it happens to use Murmur hash 2, which is pretty damn well rated these days, one of the best. Also something to note is that you can tune your unordered map. So I forget the argument now, but you can determine how many buckets you want to have. So you can minimize the number of elements per bucket, so to get your fastest performance.
Yeah. The other thing to say is that iteration order is undefined.
Yes.
Yeah. So if you iterate through an unordered map, it's unordered, right? So the elements come back to you in effectively a random order.
They won't change until you change it.
Right, but just adding a single element to the hash table could potentially make everything recompute their hashes. They end up in different buckets. You iterate through, you get things in a different order.
They can't use pointers.
You can't. A pointer to.
Like pointers to.
We're talking about iterator invalidation. So as well as complexity, one of the other things that standard guarantee tells you is which operations will invalidate iterators and pointers to elements. And yes, that's another one of the differences between map and unordered map, is in terms of iterator invalidation. Oh, we're nearly done. You wanted to talk about container adapters. These are not very frequently used. I'll rush through this. But basically, they take an existing sequence container, so usually a vector or a deck or something, and they wrap it in a new API that's more restrictive. It only has a few functions. The adaptive classes aren't actually containers themselves. They don't have this begin or end. which renders them kind of pointless in my book. I don't know why you would choose to use them. But nonetheless, I'll tell you what they are. They're standard queue, which you give it a vector and it turns it into a first in, first out queue. So that means you can push an element to the back of it, pop it out. Stack is the same, it adapts the container into a last in, first out stack.
Why can't I use a vector?
Well, exactly.
I don't get it. No.
Yeah, exactly that. Yeah. All this does is call vector methods for you.
I don't know, maybe it's optimized or something.
It's not.
I don't see how
It's contract enforcement.
Yes, that's what it is.
Okay.
So I've used, out of those three, I've used Stack before precisely because I've said I want to just get the most recent thing I've stored. And I want to make sure no one else comes along and bugs with that.
Why didn't they just implement an estimate stack?
Well, this is the standard stack. What would be handy though is if it had begin and end, so you could still iterate over the things in the stack.
Oh, I thought you said you have to pass in another container to it.
As a template argument.
Right,
yeah.
I see. Okay. No,
so you can have a stack that's built on top of a linked list.
It defaults to
I've no idea why you'd want to, but
you can override it as well. It's fine.
Okay. So you're not actually passing data, you're just passing the type.
Yeah. And there's this thing called a priority queue, which gives you constant time access to the largest element. Basically, it keeps your vector, the underlying vector, semi-sorted. So just sorted enough that it remembers what the biggest element is. So that's the container adapters, mostly just to tell you that they exist. I need a drink. Standard algorithms.
Do what you drink, please continue.
It's okay because I haven't got much left, and then you're going to have about half an hour to implement some algorithms yourself. So standard algorithm contains 80, I think it may be getting close to 100 now. I didn't really want to sit and count them, but there are lots and lots and lots of different algorithms.
I mean, it'd be ON to sit there and count them, obviously.
Yeah, that's exercise 1 this evening. They're mostly in the header algorithm. There are a few that are in numeric, ones that are particularly appropriate for numeric computing. I have no idea why they're not in algorithm. They should be, but they're not. Standard accumulate is the particularly useful one that's in numeric. There was a CPP reference, a guy did an hour-long talk just on standard accumulate and the things you could do with it. It's
like reduce in other languages? Or
left fold in functional languages.
Yeah, okay.
Is accumulate. Yeah. So the algorithms, in algorithm at least, they range from very simple ones, so standard count is about the most basic one I could think of, to the very, very specialized one, standard sort, that does all sorts of clever things to try and be as fast as possible. So you can, in fact, in a minute you'll see an implementation of standard count. You can do that pretty easily. You're going to have a challenge writing standard sort yourself in a way that's as efficient as they do it in the standard library. General advice, best advice, use the standard library algorithms whenever you can. Whenever you find yourself writing a for loop and doing something non-trivial, try and look at it and see whether you're doing something like standard count. Rather than going, for auto I in container, if I equals value, increment my counter, well that's standard count. And by using the standard library instead, first of all, you avoid bugs because you can be reasonably sure that your standard library algorithms don't have bugs. Reasonably sure. They're potentially more efficient, certainly for things like standard sort. You'd have to work very, very hard to write a sort that's better than standard sort for the general case. It promotes code reuse, which obviously everyone likes code reuse. And it also signals your intention. So somebody later coming along reading your code doesn't have to step through your for loop, working out what you're doing. It can just see, oh, you're using standard binary search. This is a binary search. Use the standard library algorithms whenever you can. And a little note, literally the small print. If you find yourself writing a non-trivial for loop. See if you can abstract the fundamental algorithm out of that into some reusable operation. This is not my advice, this is a guy called Sean Parent, did this fantastic talk a few years ago called C++ Seasoning. I really, really recommend you go and find this talk online. It's on YouTube or whatever the Microsoft one is. Really brilliant talk that really sort of changed the way I looked at standard algorithms. So highly recommend. If you've got a spare hour, don't listen to me, listen to Sean Parent.
Was it CPP?
It wasn't CPP.com, it was cloud, it was Microsoft going native, which was sort of the precursor to CPP.com. I was going to talk a bit about predicates, but I won't waste too much time on it, but basically many standard library algorithms let you pass predicates. A predicate is just a function that returns a bool. When I say a function, I mean a callable, so a function or a function object or a lambda, which returns a bool. And if you look in the documentation, some algorithms take a unary predicate, that's a predicate, takes one argument, returns bool, and some binary predicates.
So all predicates need to be boolean, and you cannot have something which returns...
something which converts to bool.
Okay.
Something which converts to bool. So, just to give you an example of how to use these algorithms with your own custom types, we have our struct person, which is the first name and the last name, and we have this function, compare person. And what it does, it says, if the last name is equal, we'll sort on the first name, otherwise we'll sort on the last names. So, it's written backwards, but the intention is we sort on the last name first, and if the last name is the same, we saw on the first name. Make sense? So then we define a vector of person called people. We imagine we fill it with data from somewhere. So then we call this function standard min element. And if you look that up, what that does is it returns you the minimum element in this sequence according to the comparator you give it. So we call min element with the whole range, so people.begin and people.end. People is this vector here. So we pass the whole range of this vector into the function, and we also pass it a comparator. And the comparison function we give it is this. So what min element is going to do is it's going to run through and it's going to compare pairs to find the smallest thing in the set according to our definition of small.
Alice Aiden, I don't know.
Sorry?
Someone's name is Alice Aiden, basically, like someone's name again. Aiden.
Yeah, Adam Aardvark
Yeah,
or whatever,
Adam
yeah.
Aardvark.
Yeah.
Also, you can use a lambda instead of compare person. Mention pass it a lambda.
Yes, you can. If only there was an example of that. So min element returns us an iterator, and then we can dereference the iterator in order to get a reference to the person.
Using a lambda is slightly more performing because I don't do a declaration, or is...
I wouldn't expect it to make a difference.
Okay.
Using a lambda might be more convenient because you can obviously capture stuff, but I mean in this case it's...
Okay, in this case it can see the definition of the function, so it would be able to inline this, but if this was defined in a different translation unit and it only knew the signature, then
using some optimization,
then potentially a lambda could be more efficient. But using a free function allows us to use this compare person function for other purposes. For example, if we wanted a standard set, you can use this function as a comparator in a standard set. So you can have things ordered by this comparator.
It's also more readable.
Yeah, arguably.
Compared to a lambda inside.
Yeah.
you don't have to define the lambda as the third argument. You can have auto predicate equals then lambda, then just pass a predicate. But depends what you want to do. If you want to capture stuff, it's not going to be an idempotent function. You might get the lambda.
It's, by the way, I'm nearly 2 hours in, and this is the first bit of C++ you've had today. That's got to be some sort of record. Yeah, came to Algorithm University, London University. Come on. So, what does a standard algorithm actually look like? First of all, they're all function templates. And they're all templated on the iterator type. Now this one, I'm showing you an implementation of COUNTIF, which is actually one of the algorithms in the...
Just on the previous slide, one note, if you pass an empty vector there, you'd need to check that your iterator wasn't .n, I believe, or you would just do...
Yes, that's why I explicitly had the line saying fill vector with data. Because otherwise it would have looked bad, yes. Although, actually, if we do go back to it, come on.
Did you have an statement for the dereference?
No, I didn't, because I know the vector has got things in it.
Yeah, it's got things in it.
Yeah, but let's say we hadn't filled the people vector, this was just empty. Min element is still going to work. Min element itself will be fine. If it's got nothing in it, it does nothing. There's no minimum element for it to return. So what it's going to return is end. It's going to return this thing that you gave it. It's going to return the one past the end, the invalid value. Right, but dereferencing the end pointer, this is Ollie's point, dereferencing the end pointer, technically we should have made sure, before dereferencing, we should have made sure that iter is not equal to vector end.
So if you didn't use auto, you would get an error.
No, auto just means deduce the type, and the type of this thing.
If you didn't use auto, you would have put, I don't know, person, iter, blah, blah, blah. So
I would have said standard vector person :
okay.
iterator in this case.
Okay.
Right, so
Alternatively, you just do person and first person equals star student element, blah, blah, blah.
yeah.
But again, UB if you don't check.
So you're going to be implementing some algorithms in a minute. So I may as well show you what one looks like. So they're all function templates, and they're all templated on the iterator type. This is the generic programming we were talking about. They use generics, C++'s version of generics, which is templates. This particular algorithm also takes a unary predicate. This, I've spelled it out. Unary predicate is just a label. It has no particular meaning to the compiler. It's just for people who are reading this code can see what sort of thing I am expecting for that parameter. So we initialize a count as 0. No. And then we have this line, well, first is not equal to last. So first and last are iterators. First points to the beginning, last points to one past the end. It's conventional to call them first and last, even though last represents one after. It's just convention to call them first and last. So, well, first is not equal to last, do something. And we say, if predicate of star first. So remember, predicate is a function, or a function object. That means it's callable. And so we call this function with the value that first is pointing to, with star first. And we know that this is a valid thing to do because we've checked that first is not equal to last up here. So we know that it's valid to dereference this thing.
Can you use a for loop?
Yes, I could.
Yeah.
If we know that predicate returns a bool or something convertible to bool, so we can just put it straight in the if statement. So if the predicate is true, we increase our count. So count if counts for how many elements in here the predicate is true. So having done that, we nudge the iterator forward one place, so the iterator is now pointing to the second element in our set. Again, we compare it. We say, have we reached the end? No, we haven't, so we go through again and again and again until we bump the iterator until it meets the one past the end. In that case, we skip the loop entirely, and we go straight to this line, return count.
Would it work in C++ if you put a pred asterisk first plus plus, skipping the increment later?
If I said what, sorry?
in the if condition, you could do no.
Star first plus plus, yes.
Yeah, would it work? Okay.
Yes. I did it in 2 lines just to,
no, just my curiosity.
for educational purposes, but yes, you could do that. Star first plus plus.
Okay, cool.
But is that considered a good way to write code?
No. I mean, use parentheses on it, because one thing that can really bite you in the ass is obviously order operations. But it's unclear if is it dereferencing first and incrementing the result, or is it incrementing and then dereferencing the result? Yeah, you use parentheses.
Isn't it very basic if the plus plus after is executed later? So
Depends what you're looking at your code.
Yeah.
Okay.
Also, if you want some algorithmception, you could use the for each. That will literally do the while first.
Well,
Did I read your mind?
not quite, well nearly.
Oh, okay.
There's another algorithm, it's called count. And count says, tell me how many things in this sequence are equal to this value. So just to show you another implementation. I've made this implementation C++11 compatible. So we need to get the value type of the container, or technically the value type of the iterator, for which we have to write this horrible ugly thing. C++14, you don't need to do that, but I don't really know why, but I decided to make it C++11 compatible.
It's a nice alias, so you don't have to write oral crap all over and over.
Yeah. But now we can write our count algorithm our count function in terms of countif. We've written countif, which is the more complex version, but we can just write count using countif. So we pass the first and last iterators that we were given, and then we've got this lambda. Lambda captures this value, captures the value by reference. Right, yeah. And then this is a predicate. So it's a unary predicate. It takes one argument. The argument is of the iterator's value type. So this is the type we get when we dereference an iterator. And within the body of the lambda, we say, is the element's value equal to this fixed value that we got up here?
You could just use const auto ampersand.
That's what I was saying about C++14.
Oh, sorry, you said okay, yeah. Sorry. Okay.
Yeah. So this is because I want to show you an example of passing a lambda to a standard function, to a standard algorithm. So using a lambda as a predicate would look roughly like that. And it also shows you how you can use one algorithm to implement another. Oh, that was a phenomenal amount of talking, but thank God I'm done. Now you can have a go. You've only got 20, I've yapped for so long, you've only got 20 minutes to do this. However, it's much easier than last week. So last week I gave you a bit of a beast of a task. It wasn't very nice. This one should be much more fun. You get to implement some standard algorithms in much the same way that we've just seen countif and count. That's not too difficult, hopefully. So with this algorithms exercise, there are some algorithms for you to implement. The only one that might be tricky is standard transform at the end. If you want to cheat, I may as well tell you, CPP reference is brilliant and has a sample implementation of just about every algorithm. So if you are really stuck and wondering how to do it, where do I begin? You can go to CPP reference, losing my voice, and it will give you a sample implementation. I'm going to have to get some water, but
yes. If you want to cheat, you could just call the stud and then the finger.
Oh, that's the word cheat, yeah.
I like his approach, more efficient.
Yeah, it's a very efficient cheat.
So, excuse me for a moment, but if you have any problems, ask Ollie, who has just seen this code and never seen it before.
Oh, no. Happy to come on.
Can I get a key?
Send me an email.
Did you repartition it? What when you can? Did you generate an NLD?
Yes.
Did you regenerate food crops too?
I think I did.
MK config is quite MK config. Just look at the history. Don't forget to mount /boot.
Apologies for yapping so much today. I really didn't expect that was going to be 2 hours of me talking. That was,
that's not a problem.
I thought I'd do an hour of talking and give you an hour to do the exercise. That didn't really work out. You done it already, Justin?
No, I haven't handled it. I had some sort of problems.
Are you running his VM?
No. Well, OpenVPN version.
All right.
It's all right, carry on.
Is it?
Well, give it a try.
Okay.
Unfortunately, you're going to fail all the tests. You're right up to the top.
That failed or not?
That has failed. Your implementation of count is incorrect.
When you go to the project,
Just open project. You will. Tom off.
So you had a ping on your mobile from the email?
Huh?
So you had a ping on your mobile?
Do I have pin on my mobile?
You had a ping
Ping?
Ping.
on your mobile from your email?
No. One of the rules of the happy person, never ever have to, ping when the email comes through on your mobile.
Charger. You were looking.
Because I'm sending an email.
Somehow got his.
I don't know how satisfied are you with your current charger?
Well,
Yeah, you would.
There you go.
Good. Awesome. Thank you very much.
Fantastic.
I think the voltage should be higher, the same or higher.
Yeah, as long as it, well, battery's pretty screwed anyway.
Yeah.
Oh, thank you very much. Enjoy.
That's, look at the state of this one.
Yeah, yeah.
This,
there you go.
Yeah.
this part is.
Awesome.
It wants, I believe, it to count the elements that have the same one as between first and last.
basically I use this name, so count, so I assume they want to count how many.
You can't reuse a function name. You've got a variable inside the function with the same name as the function, you can't do that.
And also it's not the right thing for you to say.
I like CNT.
But that didn't work out, so yeah.
So let's see what you've got.
So basically, we're looking for the value.
So you only want to you only want to give the count things that are the same as whatever they pass there. So if you need to do a comparison, don't you?
Yeah.
So your loop is correct. You want to test every element.
I would do a for loop.
Yeah, I would. But just do the while loop, and it's easy for you. Your job is to make it correct, not make it the shortest.
Yeah, I feel like a while loop is easy to see the sequence of things it's doing.
Well, I argue in favour of a for loop in general, purely because you can't forget to increment it because you need some value statement. You just do it then.
Right, something.
Oh, this is the Pandora still.
Yes, wait. When I open
to get the value.
First is an iterator.
project, is it in
Value, yes.
No,
No.
that's fine.
I can do first, yes.
What is happening there?
That's
crazy.
You could do
Value.
This is under.
Let's close the Pandora.
Yeah.
And then on a return.
Completely starts.
Right.
I cannot increase
You
straight
can't,
away.
well, no. You're comparing the iterator to the type, which is not right. You want to get the value out of it. Bingo.
Hopefully.
I would put it in parentheses.
Do I have to
No, that's already the value.
I would put the
like this?
not one to the left with parentheses, so just make it more no. I would put the parentheses between the star and the plus. So left of the star and the plus to make it more verbose that you are.
And you want to separate the stars.
It takes a while to start. See
That's what I have, like this.
First time it was pretty big.
And now,
Oh, you guys know back here.
Yeah, that's correct.
If the first value matches, he's going to have no match at all.
Less evil exercise than the last
No,
one.
if the first value is actually
I mean, I just ground on
first iterator using
stealth
stealth
units
sort of the way just like that now you will not
iterate thing. Yeah.
The result of first plus plus is the existing value.
Well, all he's doing that now, if I put parentheses, will first increment it, and then decrement it.
Because the result of first plus plus is just a do try it. Try it. Go and try it.
If it's got a test there, that's the
so if it does, then I need to.
Plus iterates. This will increment from first, and then dereference it.
The result of first plus plus is still first. The result of plus plus operator is still the original value.
Okay, that is going to do the right thing. As long as he increments counts inside that.
So if it does that, someone needs to
You
return.
need something, because imagine you've got no elements, right? You've still got to return 0.
Yeah, so I can have out something.
Yeah.
Yeah, so
Initialize stuff. What if this while loop never runs because someone can use something essentially?
Yeah.
So
Still loading the Commodore.
We'll wait for it to do that.
do
Close that.
So we found, in this case, we found a match.
no value.
It's a count, right? It's giving it's giving you want to what they want back. If you're not a size, okay, this is the return up here, right? Size t, yeah. So size t is just an it's a type of integer.
Yeah.
And the idea is that if you want to know out of this range of things, how many of them match this thing?
Oh, so how many?
How many things?
So I don't want to return. Okay, I assume I want to. Okay,
there's another sign value to it.
Okay, that's fine. So then I want to do something. Pass and then return something.
Bingo.
Six.
One passed.
Did we?
Did you pass?
He passed it.
Yeah.
do the first element in the given range equal to only the last.
So basically, you want to find the first match, and as soon as you find it, you're done. So if you don't find anything, however, just give it back.
Okay, so that's the, just double click on that.
No, it was open it. I was checking the address
you don't need to count
check
it.
the
Why doesn't then the first, if your function has got here, the first argument in this thing will be a 2.
The result of the post increment operator, so everyone can put brackets around it, is still the value prior to being incremented.
It's going to be like that.
Resulting this. Yeah, good, okay. Yeah, so you found it, and as soon as you find one, you just want to give it.
Return, and then we want to return just the value, yes?
No.
What do you want to return?
You want to
sorry,
give
yeah,
the
just go to
iterator
edit
to it.
file. Just click on that.
So it will be the first.
No.
And just change
Well, you just incremented it.
So
You can either, and there's two ways to do it, you can either increment it later or rewind. Well, actually, no, you can't leave it, don't rewind because you can't guarantee that you're allowed to. Yeah, so, yeah.
return first.
Yeah, and
No, you just need to increase the iteration.
And then
so we have that next with return. Alright, columns, so if four in this function, give it a real.
okay.
So you don't get the first statement.
We can just
You
put a
have the
semicolon.
semicolon, just skip the first statement.
First. First. Last.
So
Edit first.
well, I just plus the pre-name, yeah, just yeah, you don't need to deal with values, so choose this one. And you're not quite right though, because
Here.
you find nothing. We've got the comments as it told you, you need to do that.
The last, so, or last if no such element. So it will be
what does the transform function do?
Okay, so it
You
takes
haven't found it.
so it's last.
it takes two ranges.
Okay.
I'll just write it on the bottom here.
Two plus.
So it takes
Definitely like and the trees.
range one and range two,
In the given range.
and that function.
Each private element returns.
And it applies the function for every element in here.
Yeah.
It takes one element from there, one element from there,
Okay.
and it
It's
calls
actually a function you can call. So
the function
even though
with
it's
those
not
two elements,
you can-
and then it puts the result of the function into a third.
Okay.
So it's very, very, very general,
Yeah.
generic
Okay.
algorithm.
Mhm.
So while first.
I would use it for it again. You can use it once.
And is range 1 and range 2 always the same size?
Okay, so we're
No.
Okay.
That's something you have to be quite careful
And
of.
we want to return the first thing that this function says, yeah, do it. This function will either say yes, return it, or don't return it, so it returns true or false. So it wants you to give it, the element.
So actually, that's something you would have to deal with in equal. That's why I put equal first.
Oh, okay.
So did you Your implementation of equal handle ranges of different sizes?
Yeah, I think I'm on the last one.
Function called pred.
Okay.
You want to check your implementation of equal returns, right? So it's going to return true or false. And if it returns true, when you call this, if it returns true, it says yes, give back the iterator we're on. If it doesn't return true, keep trying.
Okay, so.
Oh yeah. Perfect. Yeah, sure.
You can assign it to a boolean if you want.
So 1 equals words.
You can put it in if pred, yeah, just put pred in this. Well, no, call it inside. You have to have brackets in the form. And then you have to give it again when you're on. So you need to call pred, not calling pred there. Imagine that pred is a function. Imagine pred is the name of a function. Yeah, that's it. And then you need to give it the when you're on.
That will be first.
First is the iterator.
Yeah.
First is the iterator. There you go.
First, and then first.
No. If this thing says it's good, pred says yeah.
So then return first.
You seem to find this no problem at all.
I major in computer science.
Oh, okay. Oh, so all this algorithm, that was. You should probably have taught that.
Oh no.
You've just done it at university.
No.
So do you use C++ at uni?
In uni, yeah.
Okay.
Yeah. But since it's been like 2 or 3 years since I used it.
Okay.
Since after graduating, so it's good like to refresh it up.
So I hope that was right, because it's been a long time since I did all this.
Yeah.
That was all. Yeah.
No, it was quite good. Yeah.
Thank you.
Basically, you can just call find if you want to.
So I need to have a counter.
You don't need
no, actually, but I need to go through elements.
You could also just
so
call
so you've got two choices. You can either implement this from scratch, or you can actually utilise this.
What I was intending people to do?
And it's a recurring theme.
It's good.
No, it's good. It's great. No, I like the style actually. Would you rather implement this from scratch, or would you rather reuse your code?
Definitely reuse my code.
Okay, then you don't need the for loop because this thing's going to do it. Why don't you call this and we'll use a lambda there.
So
So it's basically the same. You already have first and last.
So first, yes.
Okay, guys, it's 9 o'clock, so they're going to kick us out in about 20 seconds. Next time we've got a very special session. You won't have to listen to me for 2 hours, which will be brilliant. Oh.
That's okay. I will update.
Okay. Ignore this. That's not moving swiftly on.
There's a small change into the venue, which just I just learned like a couple of hours ago.
Okay.
But I will let you know in advance. To complete today on a positive note, thank you much everybody for coming. Thank you Tristan for really great and
thanks guys.
I hope everybody will join us in the pub. Those who obviously
I need a drink after that.
Yes. So everybody see you next Tuesday. If anyone needs a CLI license, send me obviously an email. Sorry?
Nothing.
And obviously we are meeting either Thursday or Friday, Thursday probably, for lunch, and you're very welcome to join us. So once again, thank you very much, and see you next week.
Cheers.
With the end of, you would check whether or not find it.
You want to get the result.
Let me just shut down this.
I'll show you the code.
We got a cheat sheet. Yes, I meant to link to that. I forgot.
That's why I'm the wingman.